Hello and welcome to Lecture 10 of Chemistry for the Interdisciplinary Sciences. Today we're going to learn about naming organic molecules like all these ones behind me. We're going to have a look at the conventions that you use to name them, and we're going to use that prefix-suffix business that we were talking about before. So let's jump straight into the learning outcomes then. They are to describe this term functional group and recognise a few different ones today. We're going to use suffixes and prefixes as we've already mentioned, but we're going to really dig down into how we do that exactly. And we're going to use the terms methyl, ethyl, and so on to describe branched chains. We're going to use numbers to tell us a little bit more about the structure of a molecule. And we're also going to recognise a new functional group, an arene, which has sort of come up already a little bit, but we're actually going to name it today. So let's have a look. What is a functional group? A functional group is an arrangement of elements in a molecule that gives you an opportunity to do something. So by that I mean, for instance, we've got this alcohol group, this OH, that makes a compound more soluble in water. So sometimes when you're designing a drug, you want to be sure that it's going to dissolve in the blood in the first place. So I was in a group where we designed drugs that reacted with water and oxygen and became inactive. That's not a very useful drug then, is it? If you can't put it in the blood, what's the point in having it? Some groups like this NH2, that also helps with water solubility, but it also gives an opportunity for connecting it to something else. So perhaps you're only halfway through making your molecule and you want to connect it to some other things. That's helpful. We've already seen alkanes themselves, chains and rings and things like that, which provide the sort of skeletal backbone of the compound itself. It's so skeletal, it's so fundamental that we don't even bother naming carbons when they show up in the molecules themselves. And hopefully, if you're not sure about that, pop back to the covalent bonding lecture just to check that the skeletal structures make sense to you. And then you also have things like this double bond here. This carbon-carbon double bond restricts rotation, so maybe it's going to lock a molecule into a sort of cup shape rather than a sort of S shape. It's quite tricky to do there, but a cup rather than an S. And that too can be really helpful to lock it into that position. That also provides an opportunity for adding certain molecules to the compound that you've got already. So in here, what we have then is a sort of alkane backbone. We have an alkene here in the middle. We have an alcohol over there, the OH, and this is called an amine, this NH2. But we'll go through this a little bit more slowly. So let's just start with the ones we've already seen. We've already seen these alkanes, and I'll remind you that the suffix that we use here, so whenever we've got a molecule, we use the prefix to say how many carbons are in a chain. We might also describe if there is branching or anything else like that. But then we say at the end of the name of the molecule, whether it's an ane, an ol, an amine, an ene, anything like that. So these all have the suffix ane for alkane. Alkanes are basically just covalently bonded molecules of hydrogen and carbon that have no double bonds in them. We already talked about the general formula, CnH2n plus 2. That is the formula that just comes out whenever you have carbons that can form 4 bonds, but they're bonded to carbons on either side in there. And don't forget we have our H's on the end. Notice that these two representations are exactly the same. So here we've got the CH3 group, just been called CH3. We could also call that a CH2 there in the middle, so you can write it in lots of different ways. And also a reminder that this skeletal structure means the same thing as the thing up there, and also represents the shape of the molecule a little bit better too, which is why we tend to use it. And that's why that's going to be the primary means that I'm going to display molecules to you on this course. So let's just go back through that prefix business, looking at where the longest carbon chain is, and that is the most important part, finding your longest carbon chain. Once you've found it, it gets the prefix meth, eth, prop, bute, pent, hex, hept, oct, non, dec, and so on. And they are included on this table. You do have to learn them. You only really need to learn the first 4 because after that it's just shapes, pentagon, hexagon, heptagon, and so on. So hopefully you're used to those. And there I've shown you a few examples. So there's a carbon chain of 3, it's propane, a carbon chain of 4, that one's butane, and a carbon chain of 7, that one's heptane. So how about if it's a little bit more complicated than that? what if there is a branching? What if there are more carbons? It's not just in a straight line, they come off the main chain. Well, you still find the longest carbon chain. And what we are going to say about both these molecules is, oh, it's a type of butane. And the way that we know that it's a butane is we're finding our longest chain. So here it's 1, 2, 3, 4 carbons along. I could also have counted that one going around as well. Doesn't really matter, whichever one works. So here we got our longest carbon chain is a 4 carbon chain, and that makes this a butane. But notice that there is a methyl group. So what do I mean by methyl group? I mean a carbon that is a chain of 1 carbon, really, doesn't it? So methyl is 1 carbon, ethyl is 2, and so on. In this case, because we got this methyl, we're saying, okay, it's a butane, but it's a methyl butane. Just like we would say it's a bus, and then we'd say, oh no, it's a green bus. It's a big green bus, where we're doing the same thing here. So this is a butane, but specifically it's a methyl butane. And then we're going to go one more step and say, well, where is the methyl on the chain? Now, for methyl butane, there is actually only one possibility. It can only really be on the second carbon in from the end, because if we took that molecule and turned it around, so I'm thinking about this one here, if we rotate that in physical space, it would look like it was on the 3 position. But anyway, here then we're going to say, okay, this is butane, and I have a methyl group, a 1 carbon chain on the second carbon along. Hence, this is 2-methyl butane. So let's follow that process again for this second one. So the longest chain, yep, that's here. So I've got 4 there, and then I have a methyl group here, and I have a methyl group here. Okay, so now I've got butane, but it's got 2 methyl groups on it. The way we say that is it's a dimethyl group. So we'd say methyl if it was 1, dimethyl for 2, trimethyl for 3, tetramethyl for 4, and so on. Again, this will be laid out a little bit clearer in the workshops that are coming. So here we have to say where the methyls are, because we could have this hydrogen here could also be replaced with a methyl, but it hasn't been. So here we have a methyl on the 2 and the 3. Hence we say that this is 2, 3, so it's 2, 3, and then a dash, dimethyl, 2 methyl groups, on the butane backbone. 2, 3, dimethyl butane. The most fun thing to do when you're drawing these and naming them is to make sure that you always say it out loud, because it's always a lot of fun. Well, at least this counts for fun in my world. So notice that I mentioned that you could count around the corner. So if ever counting around the corner leads you to a longer carbon chain, then you should absolutely do that. Always count around the corner. You never know if the molecule has been drawn the right way for you. So here you can see that if I count the molecule from that top carbon instead of the, sorry, I'm talking about this carbon instead of this one, then I still get 2-methyl butane. If we look at the numbers, it's still a 4-member chain. I've still got a 1 carbon chain off the second carbon. And the same is true for the next one. So that's why it's important to always find your longest carbon chain that will lock everything into position. Okay, so let's have a look at this one here. Now you might think, okay, so I've got a 4 carbon chain there. That's a 4 carbon chain. And off the third carbon, I have a 2 carbon chain. So you wouldn't be wrong necessarily in calling this 2-ethyl butane. 2-ethyl, ethyl because it's a 2 carbon chain, 2 because it's hanging off the second carbon along. Now there, you might be saying, how's that the second? Because I can also count from this end. And generally we try to give it the lowest possible number. So I could also call it that. But hopefully you've noticed that if I count around the corner, there is a longer molecule to be had. Look there, there's actually a 5 carbon chain. That makes this so much easier. So now we've got a 5 carbon chain is a pentane, meth, eth, pro, but, pent. And then there's a methyl group on the the third carbon along. That makes it 3-methyl pentane. Hopefully that makes some sense. If you had written in some form of assessment situation 2-ethyl butane, as we had before, we would still mark that correct. It's just you're trying to do this as correct as possible, and so we need to count around that corner. Now, on the last one there, we can see that the methyl group was right there in the middle position. But if now, instead, we have that methyl group further along, you might think, oh, that's 4-methylpentane, and you'd be right, that would be an acceptable answer that we would mark correct. But technically, we could number it the other way around instead. And the lowest possible number, when you're writing something, the lowest possible number is assigned. And I'll go one step further on and say the lowest number is assigned to the functional group, if possible. Here, there isn't really anywhere to say that bit is an alkane, so we should number these instead. So instead of going 1, 2, 3, 4, 5 along there, 1, 2, 3, 4, 5, we're instead going to go 1, 2, 3, 4, 5 backwards. That means now that the methyl group is in the second position, it's on the second carbon along, and thus it's 2-methylpentane. Again, we would accept 4-methylpentane, but we might as well learn how to do it right. And remember that this molecule we could flip it around in physical space, and once it's flipped around, it would be indistinguishable between the two. Okay, so this general formula, does it still hold up when you've got branched compounds? Yeah, it absolutely does, because what's happened is we now have a carbon that's missing a hydrogen. So this carbon here, that is the branched carbon, I'm looking at this one, has one fewer hydrogens than it should be, but it's okay because we've got a new end carbon that has one more hydrogen than it should have. And so the general formula will still apply when you have branched compounds as well. So those are the formulas. Notice they all work out. If C is 1, then Cn plus CnH2n. 2 lots of 1 is 2, plus 2 is 4, 2 lots of 7 is 14, plus 2 is 16, and so on. Now, all of these molecules have the same molecular formula. If I count up the number of carbons and hydrogens, they're all C5H12, and we call these isomers. So isomers is where you've got the same number of atoms of each element together, but they're now in a different order to what we had before. That being the case here, look, we've got some different names. So we've got pentane, that's just a straight chain of 5 carbons. 2-methylbutane, that's a chain of 4 and 1 hanging off. And then we got 2,2-dimethylpropane. So let's just go through that one and make sure it makes sense. 1, 2, 3 is the propane. And on the 2, I have 2 methyl groups. That works out. You might also have counted it top to bottom. You would still get the exact same answer as before. So there we go. Isomers are 2 compounds with the same molecular formula, but a different arrangement of the atoms. And we're going to use that term quite a lot as we go forwards. So that is our general alkane. Now the thing is that, of course, we sometimes need to just say, well, this is the important part of the molecule, and then something else is added to it that we don't really care about. This is how we use the term R, an R group. So an R group here can sort of be anything. It's just a way of saying, and then the rest of the molecule. If you are using it in an exam or an assessment situation, you should always define what it is. But it could be as simple as a hydrogen atom, or it could be a complex chain or a ring, or some fused rings or something like that. So when you see the term R there, it just means something is attached to this. And usually we're talking about a carbon chain of some form. So there we go. This is the very first one in our functional group toolkit. We are going to fill this up as we go through the whole course. So let's get to our next one. Alkenes now are very similar to alkanes, except for they have double bonds in them. And having the carbon-carbon double bond means that it's restricting that rotation that we mentioned before. It gives it an opportunity to attack. It has pi electrons. Those of you who had a look at the hybridization lecture. So here are 2. Now this time the general formula is CnH2n, no plus 2. Why is that? Because by putting this double bond in between the carbon, my carbons have lost a bond that was originally attached to a hydrogen on both sides. We used to have a hydrogen on that carbon on the left and one on the right, but now we don't have any. And that's why it's just CnH2n. So, yeah, alkenes contain carbon-carbon double bonds. Let's have a look at some possibilities for butene. So we still are naming everything after the longest carbon chain. So in this case, that's bute. We got 4 there in a ring. If I turn that molecule around, notice I've got the same as the one on the other side there. And the way that we name these molecules is we say where the lowest numbered carbon that starts the double bond is. So here on butene, our double bond, our alkene itself, is there starting on carbon number 1. Thus we call this but1ene. Over here you'll notice that we've got the carbon-carbon double bond on the second carbon along. And no matter which way we number it, whether we go 1, 2 that way, or we go 1, 2 that way, we still have the double bond starting on number 2. Hence we call this but2ene. Now the number always immediately precedes what it's describing. So here, the number is talking about where the alkene is, and therefore we have but2ene. It's saying, oh, the ene is in the 2 position. So if I flip that round, that is but1ene again. It's just I'm numbering it from this side instead. So 1, 2, 3, 4. However, if you called this but3ene, we would still accept that as a correct answer, but you might as well know how it's done properly. And that's because the lowest possible number is always assigned, as it says at the bottom of the slide there. Okay, your turn. Let's have a look at this one. So I want you to work through this using the process, and I want you to think about, is it answer A, B, C, or D? So give that a go now. Okay. If you need more time, hopefully you're going to pause. But let's have a look. Now we've got 5 carbons in a row. The longest chain I can see is this one along here. Now, I might number it from this side, from the left to the right, but I'm noticing that this double bond is closer to this right-hand side than the left-hand side. And so I'm going to number it from this side first. 1, 2, 3, 4, 5. Lovely. So I know it's a pent, first of all. So that already rules out A and B, because we know they're pents. I do not know why it does that. So we know that this is a pentene of some form. Where is the ene? It's on the 2 position. So this is pent2ene. So we're looking pretty good for answer C over there. And finally, we're going to say, and there's a methyl group here on the second carbon along. So if that's the case, then this must be 2-methyl pent2ene. And so C is the correct answer there. And hopefully you got that as well. Now, why might you have said 4,4-dimethyl but3ene? Well, maybe you counted it like this. 1, 2, 3, 4. And then you said, and there's a methyl group there, and there's a methyl group there. So I, again, would mark that correct in that you have managed to describe the molecule using the naming conventions, but technically we should be looking for the longest possible chain. So please do try and find that longest possible chain. And that's basically it for the alkenes. It's the same as the alkanes, just you now have to name and say where the ene is, and the ene can move around the molecule. Okay, let's have a look at our next one. Our next one is an alcohol. So the reason we're putting these in our toolkit is because we are going to have to eventually learn them. An alcohol has an OH attached. So now we've got that little, you remember the oxygens that we saw earlier on in our molecules? And we also saw an OH in the aspirin here, didn't we? So there's our OH, there's our OH at the end there. That alcohol functional group is really useful for lots of reasons. It's a nice connecting group, it helps water solubility, it helps it become a liquid in the first place and join to itself. It's a really, really nice group because ethanol is a liquid, whereas ethane is a gas. So again, we're going to name the longest chain. We're going to make sure that we can give the lowest possible number to the functional group we can. And essentially we're using the exact same rules, so let's give it a go. Here in these molecules we have, first of all, I've got a chain here. Now again, my temptation is to number it from left to right, isn't it? Just because I read that way. But if I came from a different country, I might read from the right to the left, especially like an Arabic script or something. So I need to look at where is my functional group, and it's there, isn't it? There's the OH on this side. So I'm going to number from that carbon over. So it's 3 carbons long, it's a prop. And yeah, we got the same thing going on here. I'm going to number in the same way just because there's no difference in this molecule. This OH is in the middle, it's equidistant from either side. So this is a prop for a start, and because it's an alcohol, because it's got that OH group, it's a propanol, I know that much. So we've got propanol, and finally we have to say, where is the OH attached? So in the first one, it's attached on the first carbon, hence propan-1-ol, and the second one, it's in the middle, so propan-2-ol, there. Okay, what if you have several functional groups? So you could have more than one double bond or more than one OH. Let's have a look at a molecule like that. Here we got propan-1,3-diol. Why is it that? Well, again, we can look at our carbon chain. It's going to make no difference whether I number left to right or right to left here. And notice I have an alcohol group on the 1 and the 3. So here, just like when we had 2,2-dimethyl or 2,3-dimethyl, I'm going to say the exact same thing, but I'm going to say it's a diol. And I could also say a diene or a diamine. So I can use the terminology di, tri, tetra, and so on in all naming schemes as well. So this is a prop because it's a 3-carbon chain. It's a diol because there are 2 OHs, and those OHs are on the positions 1 and 3. Thus it is propan-1,3-diol, or propan-1,3-diol if you prefer to make it sound nicer. Now this leads us to a series of ideas about alcohols, which is primary, secondary, or tertiary. Now, what you do not have to do in a name is say whether it is primary, secondary, or tertiary. I'm just showing you this while we're on our way. We are going to return to this right at the end of the series anyway, to find out why this is important. But essentially, a primary alcohol is one where the carbon that's attached is only attached to one R group. Or another way to think about it is, it has 2 hydrogens. So we might think 1 R group, or we might think 2 hydrogens. Remember, an R group tends to be a carbon chain or something like that, not usually a hydrogen. A secondary alcohol has 2 R groups. Or another way to think about it is it has 1 hydrogen attached. And finally, the tertiary alcohol that has 3 R groups attached. Now, why is this important? Because sometimes the chemistry involves changing that CO single bond into a double bond. So sometimes we want to transfer it. Maybe we want to make it less soluble in water, or maybe we want to connect it in a different way to the molecules, to some other molecule to make our drug or something like that. So let's have a look at an example here. Now, do we think that this is a primary, a secondary, or a tertiary alcohol? So I want you to look back at that last slide and have a look at this compound and make a decision one way or another. So give that a go, pause that. I'm assuming that you have, okay. So let's look at this carbon. The carbon that is attached to the OH is here. So I'm looking at this carbon, and I'm noticing that I could say I've only got 1 hydrogen. Again, please forgive that little line. I think it's because it's on the periodic table. Or I could say, oh, I've got 2 methyl groups attached. So I've got 2 R groups there. That being the case, this is a secondary alcohol. So the fact that I still have 1 hydrogen means I must have 2 things that are not hydrogens, essentially, and that's why it's a secondary alcohol. Again, we're going to return to this later on. This is just priming you for that change. So let's pop alcohol into our table now. And we're going to finish off the top row here with an amine. Amines are exactly the same as alcohols, except for we use a nitrogen instead of an oxygen atom. Again, it has lots of possibilities, but one of those possibilities is that it can use that lone pair electrons, on the nitrogen to make it act like a base, for instance. So we can have these compounds be proton acceptors, and sometimes that's useful in a reaction, or we can use that as a connecting group. It increases its water solubility. All of these different things are very helpful to us. So again, we use the same process. We name the longest carbon chain, and then the suffix is amine. So that's basically it. We don't really need to go through some examples of that. It's exactly the same as the alcohol, so I could say diamine. Right here I've got ethylamine. I could say ethyl 1-amine if I wanted to, but if it's only a single amine, then it's got to be on one of the end carbons, and they're both end carbons there. So sometimes you don't have to say a number if there's no possible way to arrange the molecule otherwise, but again, if you did it, it'd be okay. So you might as well, again, learn the right way to do it and just give it your best try. So there we go. That fills out our top row. So let's now take some time to work on these. So I do want you to work on each of those on your own. Please do pause now and give them all a name. And then we'll come back and go through it. If you want to come back after you've done C and listen to the first few answers, feel free. Whatever works for you. Okay, I'm assuming that you've gone away and come back, so let's have a look. On the first one, A, it isn't a branched alkane, but it is just an alkane. There's nothing interesting on there. There's no double bonds. There's no unusual atoms. By the way, when there's a named atom in there that's not carbon or hydrogen, we tend to call it a heteroatom. So just FYI, you might hear that term as you carry on in your degree. Okay, so I'm going to count here. 1, 2, 3, 4, 5 along. Okay, that one's pretty boring then. That one is just a pentane, isn't it? Okay, I can see that. I can see that that's not going to work. So let's just say them out loud, and then on the next slide you'll see all the written answers. So A is pentane. Let's look at this one. For B, I'm going to number it from the side closest to the functional group, which just happens to be the left this time. Okay, so I've got 4 carbons in the longest chain. This is a bute then. It's a bute root, which is hard to say. But we know that the suffix is going to be ol because I have an OH. So OH is ol. I've also got a methyl group here. So if we got a methyl group there and it's an ol, then this must be 2-methyl butan 2-ol. So hopefully that makes sense. 2-methyl butan 2-ol, because I got a 4-membered chain. Oh, did I say 2-methyl? 3-methyl butan 2-ol. I think I said that wrong. 3-methyl butan 2-ol there, because the methyl is in the 3rd position along. Apologies if that confused you for a second. Let's look at C. Okay, so I can see that the alcohol is over here, but it isn't alcohol, so I'm going to say ol. Now, really common mistake in these situations is to count the oxygen as a carbon. It isn't. The first carbon is this one here. So just be really careful. It's very common for people to count that one. So don't worry if you did, but now that you spotted it, let's correct that. So we've got 5, 6, and 7. Okay, so this is a hept, and we know it's a heptan ol because the OH is over there. In fact, we know it's a heptan 1-ol, don't we? So we're doing quite well there. And finally, we know that we got a methyl group on the 2nd position along. So that is going to be 2-methyl heptan 1-ol. I'm just going to slide that over there. 2-methyl heptan 1-ol. I'm just noticing in my answers that I've written pent instead of hept, so I'm going to correct that. Lovely, let's go to the next one. So what functional group have we got? We've got an alkene, but I can see that the functional group here is closer to this side, so I'm going to do 1, 2, 3. Okay, so this is a prop. It's a propene because we've got the alkene, the double bond there, and it's prop 1-ene. Now, you don't need to say prop 1-ene because it couldn't possibly be prop 2-ene. That would be the same thing, wouldn't it? I'd just count it from that side instead. So that one's just propene, is what I would say. Okay, what have we got here? We've got an amine. That's the NH2 group, the amine in the middle of the chain. So I can count from either end. I biased towards this way, so I'll do it this way. 5. Okay, so this is a pentamine, I know that. And it's a pent-3-amine because the amine is on the third carbon along. Finally, what have we got here? The functional group is over here on the right-hand side, so I'm going to count from this carbon. 1, 2, 3, 4, 5, 6. Okay, I've got a hex. I've got a hexene because I've got a double bond there, and the double bond is on the second position, so this is a hex-2-ene there. Lovely. So let's write up those answers a little bit more clearly. Pentane, 3-methyl-butan-2-ol, the methyl group's on the third, the ol is on the second. 2-methyl-heptan-2-ol, again we're counting those carbons along, we're seeing 7. We've got propene down at the bottom, 3 carbons, pent and 3-amine. Now, really, you don't need the an. You can write pentamine if you want there. So if I went back and fixed that, I probably would just actually write pentamine. That would make more sense. There we go. Boom. There we go. That's nicer. And then we got hex-2-ene there in F as well. Lovely. So the last thing I want to go on to is just to talk about arenes. Now, you don't have to name arenes or anything like that. I just want to show you them because they're going to crop up every so often, and it makes more sense to do it now while we're thinking about functional groups. Arenes are really nice because they are ring structures. So now we've got a 2D shape, not just sticks. So far we talked about having alkane chains in there and maybe using alkenes to stop them rotating. Now we also have flat ring systems here. You might see them drawn in these two different ways, but please be aware they mean exactly the same thing. And they can be used interchangeably either way. The reason that we use the left-hand structure quite often in chemistry, and I would personally, if I were drawing a ring, an arene ring, I would draw it like this, making it look like it's a sort of triene of some form, but actually it's not. The electrons are delocalized around the whole ring. So I'll explain what I mean by that in a second. But the structure on the left is much easier to count when it comes to hydrogens. So if I were to look at each carbon, I would say, okay, this carbon here only has 3 bonds, double bond, and that single bond is 3, plus 1 more, because we know carbon always makes 4 bonds from the periodic table. And so what I'll find is that on each of these carbons, there is a hydrogen. On this structure, I just have to know it. I just have to know that the hydrogens are all 1 each on the ring. And to be fair, you will eventually very quickly learn that. But we might as well use the left-hand structure because it helps us figure out what's going on with the electrons. So there we go. It looks a little bit better. Now, the problem with the left-hand structure, and the reason why you might not want to use it, is it suggests that there are some shorter bonds and some longer bonds. And so really what I should do, sorry, I'm saying shorter, the fact that the double bond is stronger makes it shorter. So really what I should do is have a hexagon where we got short double bonds and then long single bonds, and it looks very odd. I also don't think this is going to be a hexagon. Yeah, no, it's not because I can't draw it. But you can see why it's really odd there. So it does suggest that those double bonds should be shorter. And in fact, when we actually look at the structure, so you remember we looked at it way back in the in lecture, was it 4 there? Covalent bonding. Whichever lecture covalent bonding was, I guess it's 5. We physically saw those rings from a crystal structure of tamoxifen in there, and we saw that they were perfect hexagons. So it couldn't possibly be that we got shorter bonds on 3 of the sides than the other 3. And this structure over here with the delocalized ring system does represent that it is a perfect equilateral or regular hexagon. All the bonds are the same length. The reason for that is that the carbons are all double bonded, but they have p orbitals left over in that. So if you looked at the hybridization lecture, they're all sp2 hybridized, and they have a p orbital left over. Or if you haven't, don't worry about it. Each carbon atom in this ring has 1 p orbital with 2 electrons in it. And those electrons, all these orbitals overlap to give us this sort of ring system at the top and the bottom. Now, that's useful because it makes this ring flat. Whereas if I had 6 carbons in a chain without the double bond system, they would in fact look like this. So it'd be all bendy and puckery, because you remember that our skeletal structures show that carbon chains look like that. They bend like that. If we had 6 of them in a ring, it would be a really bendy, puckery ring. And that does exist. You're going to see that in terms of sugars and so on during your degree. But arenes are flat rings there, and they're flat because of the overlap of all the electrons in the p orbitals there. The electrons are said to be delocalized. They don't belong to any one carbon. All 6 belong to all 6 atoms. Why is this useful? Benzene itself is a very useful compound because having that cloud of electrons makes it really good at absorbing energy. So it is used in an additive in petrol it's called an anti-knocking agent. So if you've ever been on a bus, a really old bus, and it's like juddering along, the reason it's juddering is because the pistons that power the engine, they compress the petrol air mixture down, they are ignited by a spark plug, and that pushes it back up just at the right time to be on a sort of cycle, if you want. When the cylinders get really bad at cooling themselves down, i.e. your radiator is ruined, or else the radiator connections are not very good, then the piston itself gets so hot that the reaction starts as the piston starts to squash it down instead of right at the bottom of its trajectory. What benzene can do is essentially cool down the reaction by absorbing energy with its electrons and promoting its electrons up. So benzene is a really nice anti-knocking agent in that, and it's usually the smell that people really like in petrol. So if you're like me and you really like the smell of petrol smells nice on its own, but the benzene is a really lovely smell in there. And in fact, these are called aromatic compounds because they smell so good. You might also be aware of cough drops. So cough drops have a ring like benzene. Now I should say benzene is specifically the 6-membered ring, and this general class of compounds is called an arene in there. So another use of the arene rings is in something like Kevlar. You might be aware of Kevlar. It is a plastic, essentially, and the plastic is made of long chains of molecules, and because it has these arene rings inside them, they're long 2D ribbons instead of being sort of strings like it would be if it was an alkane chain. We've got these ring systems which makes it 2D and thick, and they can lie on top of each other really, really densely through a process called pi-pi stacking. Again, pi comes from the symmetry of those molecules. If you watch the hybridization lecture, that might make some sense. But the Kevlar is really, really densely packed, and that's what stops it from allowing bullets through and so on. It's quite light. Kevlar is really bad though at being out in light. So whenever you see Kevlar vests or something like that, the Kevlar will be inside a black covering, because when photons hit the benzene, it absorbs that energy. It absorbs the energy and it starts doing reactions, and the Kevlar breaks down over time. If you ever go to glass blowers, they tend to have Kevlar mats without the black covering over them, and they always say, oh, and it degrades over time and you have to throw it away. It's sunlight that is breaking it down there. Okay. That's enough talking. And also, like, good luck if you're going to a glass blowing thing. It's really fun, but I can't imagine why you would be doing it. Benzene's got really, really different chemistry to the other rings, the rings that are not double bonded. And be aware that this is not a type of alkene. It's not a triene. It is its own functional group there. They're really useful, but we're going to assume that they're going to be unaffected by anything to do with oxidation. And again, we're going to see those later on, but I thought I'd just mention what they are now. Okay, that takes me to the end of the lecture. Thank you very much, and best of luck. I'll see you in the next one.